This video will cover section 2.5, part 2. So we're going to start from where we left off, which was problem 5. And what we did with problem 5 was to solve to find the zeros. Remember, that's what we said, to solve, that's what it means, to find the zeros. One thing that we did was use the rational zero theorem, and we had a lot of possibilities for rational zeros. Those possibilities were numbers like plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, and also plus minus 24. Out of those, we graphed the polynomial using our graphing calculator, and we noticed that the graph, it was only touching the x-axis at x is equal to 2. But we also noticed that the graph was touching and then turning around. So because of that, we knew that there was an even multiplicity. We verified with synthetic division that, in fact, 2 was a 0. And so we ended up getting a remainder of 0 here. And after performing synthetic division, we took the coefficients 1, 0, negative 6, negative 8, 24. And after performing synthetic division once, we ended up with the coefficients 1, negative 2, 1, positive 2, negative 2, and negative 12. Then we performed synthetic division one more time because we knew there was an even multiplicity. And after that, we obtained the coefficients 1, 4, and 6. And of course, the remainder was 0. So that's how we verified that x is equal to 2 was a 0 even multiplicity. Now, we do have a polynomial of 4th degree, so n is equal to 4. And what that tells me is that we could have 4 zeros. Now, we tried, and remember that we started with something of degree 4, then we went to degree 3, and then degree 2. So the 1 represented x squared, the 4 represented x, and then this was our constant term. So we had a polynomial that looked like this, and we tried to factor it, but we were not able to do that. So what we did was use the quadratic formula. Correct? Yes? So after doing that, we found that the remaining 2 zeros were negative 2 plus I square root of 2, and the other one was negative 2 minus I square root of 2. And I'm not sure if I did mention this in class, but anytime you have imaginary zeros, they will always come in pairs. Just like irrational zeros will. So more specifically, these 2 zeros are complex conjugates. And so that's why I wanted to repeat just go over the solutions of this problem. So remember, complex conjugates are the exact same terms, the real and the imaginary part, but the sign in the middle, one is positive and the other one is negative. Okay? So anytime you have an imaginary zero, you know that you have the other one there, the complex conjugate. So now let's go to the next problem. And so you can see here properties of roots of polynomial equations. So if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. So going back to this example here, we established this is degree 4, so we're going to have 4 zeros. So two of our zeros were the same, but as the next slide mentions, we're going to count them separately. So we had x equals to 2, x is equal to 2 twice. So I could refer to this as my first 0, x sub 1, my second 0, x sub 2, my third 0, x sub 3, and my fourth 0, x sub 4. All right? So if it's degree 4, we have 4 zeros. Now, the second statement, it says that if you have imaginary root, remember we do not call that an x-intercept because it's not really going to touch, it's not going to touch the x-axis. So if you have an imaginary root, then we will also have its complex conjugate. And so we say that imaginary roots, if they exist, they occur in conjugate pairs. Yes? So now it makes sense why I went over the previous problem again? Okay. So now we're going to look at the next theorem, which is the fundamental theorem of algebra. And it says that if f of x, do I have your notes? So if f of x is a polynomial of degree n, where n is greater or equal to 1, and then the equation f of x equals 0 has at least one complex root. Now, let's go over it again. So, remember we established from the beginning, I think it was section 2.3, that polynomials could be of degree, the degree could be any non-negative integer, right? And so, if we consider the ones of degree 0, will those be 0 and non-negative integer? Yes, it is, right? So if I were to have a function like that, what is x to the 0? It's just 1, right? So in this case, this one is just a constant function. And so a polynomial of degree 1, how do we call those functions? Linear. So linear function. So, what do you guys think? Why do you think that it says here we're restricting the theorem to polynomials that are of degree greater or equal to 1? So in this case, we're taking this one out of the question. So to have at least one complex root. Yes? Well, what if we had a coefficient here, like a 4? And this will be a 4, right? So if we were to graph it, it will be a horizontal line at 4. So will that one have a root? No, right? So that's why we're taking those out of the question. But if we consider a linear function like that one, let's say there, it does have a root, right? So that's why we have to not eliminate, but just consider, well, excluding, that would be the right word, excluding polynomials that are constant functions, all right? Those, they could, if it was on the x-axis, yeah, it could have infinitely many roots, right? But if it is something that is above the x-axis or below the x-axis, they will not have a root. But let's go back to the ones that do have a root. And so when it says it has at least one complex root, that means that there will be a solution for this equation. So there will be some x values for which f of x or y is equal to 0. Now, the word complex, will that include imaginary roots? Yes, yes it will. And so I want to remind you that complex numbers, they are the big set, and then real numbers is a subset of complex numbers. So when we say one complex root, it doesn't really matter if it will touch or not. We're including real and we're including imaginary. That's making me think about the constant function now. But okay, let's move on. So let's go to the linear factorization theorem. And if you have looked at your review, you're going to have to use all of those theorems. So you will have to go back to your notes, and for some of them, fill in the blank. Okay? So let's see. In example 5, we found, oh yeah. Yes, this one here, they're not writing 2 twice, it's just once, right? And then here, how many zeros come from here? 2, right? Because we have the plus minus. So we had 3 distinct roots because 2 was being repeated. So it was a multiplicity of 2. And that's how, that's why the graph was touching and then turning around. So now, if we were to list, to factor that polynomial, it will look like the following. So going back to example 5 and using the linear factorization theorem, we're going to do the following. So we're going to write all the factors. So we had x minus 2. That factor comes from the 0 x equals 2. Remember we had it twice, right? So it will be x minus 2, the next factor. And then we also had those imaginary zeros. So the factor will be x plus 2, and then let's say minus I square root of 2. And the last factor is going to be x plus 2 plus I square root of 2. Now, if you are wondering how I got those factors, this one came from x is equal to 2. What you could think of is like taking this positive 2 across, and if you do that, you will end up with minus 2, right? So same thing that I did here. The 0 was x is equal to, I'm looking at this one here, negative 2 plus I square root of 2. So if we take the negative 2 across, it will become positive 2, right? And then if we take this positive I square root of 2 across, it will become negative I square root of 2. Lastly, the last one, it is x is equal to negative 2. Again, looking at this one, but now at the one with the negative sign, it will be negative 2 minus I square root of 2. So if we move those terms that are on the right side to the left side so that they are with the x, we will get positive 2, and then this negative I square root of 2 will become positive I square root of 2. So those are the factors. Now, what is the leading coefficient for this polynomial? 1, right? So because of that, we could say that a sub n is equal to 1. So I guess we could say those are the easy polynomials to work with. Now, however, when your a sub n is not equal to 1, then there's actually some work that you will have to do. And that's what we're going to do on the next example. Okay, so example 6, finding a polynomial function with the given zeros. So now what we're going to do is kind of like work backwards. And so instead of finding the zeros, we're given some zeros, and then we're going to find the factors. And then after that, we're going to multiply the factors to get the polynomial. So we're finding a 4th degree polynomial. That's actually important because how many zeros are we going to have? 4, right? yeah, 4 zeros, including the ones that are occurring more than once. So here we're given 2 of those zeros, -2 and +2. So we have x is equal to -2 and x is equal to 2. So Lorenzo, tell me what will be the first factor that comes from this 0. So would it be
x plus 2.
very good. And then Chris,
-2.
x minus 2, okay. All right. Now, if you keep reading the problem, we have that I is also a 0, right? It's right here. So now we have x is equal to I. So what will be the factor that comes from that? Get in. Well, remember we need x. Minus I. Okay. And now, Crystal, since we know that imaginary zeros occur in pairs, right? Conjugate pairs, what will be the other 0 that you could imply will be there? Very good. So -I. So Emily, what will be the factor that comes from it?
X plus I.
X plus I. Okay, very good. Now, in this case, we cannot assume, so do not assume that a sub n is equal to 1, okay? That is very important. And so the reason we can't do that is because we're actually given a function value. Well, sometimes it could be a sub 1 could equal 1, but others it will not be 1. So all right, Andrea, come sit here next to Leslie. Okay. Do you have your notes for 2.5?
I don't think at home.
Okay, so you need to write some stuff. And so do you, Lorenzo. You're not just going to sit here and stare at your notebook. Come on. So get something to write with. Get your backpack off the desk. Get some paper and write down what I'm doing. Yes.
Did you need to pause the video or not?
Yeah. Oh. Oh well. That's okay. Things happen. Okay. So you have something to write with now? Okay. Thank you. All right. So what we're going to do now is we're going to multiply all 4 factors because we know it's a polynomial of degree 4. So what I would suggest you do, well, let me write this down first. So we don't know what a sub n is yet, but we know what the factors are. So x plus 2, x minus 2, x minus I, and x plus I. Okay. So now what I suggest you guys do is that you multiply the 2 factors that have a rational or a real 0. And then you multiply the ones that have the 2 complex conjugates. Okay. So if we do that, we still have here a sub n. If we multiply these two, they're actually going to give us a difference of squares. So x times x is x squared. X times negative 2 will be negative 2x, and then positive 2 times x is positive 2x, and then positive 2 times negative 2 is negative 4. So if you guys notice, the two terms in the middle will cancel out. So what I'm going to do is just, instead of doing that, I'm just going to write it as a difference of squares. And so that will be x squared minus 4. Now for this one, we're multiplying two binomials, and we know that we have complex conjugates, positive I and negative I. So I don't know if you guys remember a little shortcut that we used to use back in section 2.1. And so that was like A plus BI times A minus BI. So if you're multiplying two complex conjugates, the solution for that will be you square this term, A times A, so that is A squared. And then instead of having a negative sign here, you will have a positive sign. And then you square the coefficient of the imaginary part. So in this case, it will be B squared. If you don't remember why that happens, that is because, well, let me do the long way. This is actually a good review from 2.1. So if we multiply A times A is A squared, A times negative BI is negative ABI. Then positive BI times A is positive ABI. And then negative BI times negative, I'm sorry, I don't even know what I'm writing, times the positive BI times the negative BI, it will be negative B squared times I squared. Do you guys remember what, well, first of all, the two terms in the middle will cancel out. And then here we have negative B squared. What is I squared equal to? Negative 1. So that is where the positive sign comes from negative times negative. So that would be positive B squared. So remember, you are welcome to use the shortcut on the test. You will definitely have a problem like this. It is also on your review. So if you use the shortcut, that can save you a lot of time. So going back to this one, so what I'm going to do is take the x and square it. So it will be x squared. And then what is the coefficient of I? 1. So what is 1 squared? Just 1. And so instead of having a difference of squares, we will have a positive sign there. If you don't believe me, then you can do the long way, x minus I times x plus I. If you're not sure, or it happens that you forget the shortcut during the test, then you could do that. Okay, so going back to this thing. So now what I want you guys to do, go ahead and multiply those two polynomials. And you could do that on your own. Okay, so the answer for that, we still don't know what a sub n is. We're going to get to that in a minute. So the answer after multiplying those two polynomials is x to the 4 minus 3x squared minus 4. Here's the long version if you want to look at it. So now what we're going to do with to find a sub n is we're going to go back to the instructions where we were given an x value and a y value that corresponded to it. So we were given that f of 3 is equal to 150. So in other words, when x is equal to 3, yeah, negative, oh, thank you. So y will be negative 150. Or the function value will be negative 150. And remember that comes from here. So I'm going to make some room here. And so what we're going to do is we're going to substitute the function value of negative 150 here. Well, let me do it in steps. So f of 3, we're substituting that with the number negative 150. We're still trying to solve for a sub n, but now we know that the x value that we're going to use is coming from here. So it's going to be a 3. So for every x that you see here, you're going to substitute that with a 3. So we'll have 3 to the 4th power minus 3 times 3 squared minus 4. You need to sit up, okay? I don't want you to put your head down anymore. And open your eyes. That will be helpful. Okay, so now we need to solve for a sub n like a regular equation. So here we do what's inside parentheses. So 3 to the 4th power is equal to 81. Then we have 3 squared that is equal to 9. And then we have a minus 4. So 81 minus 27 minus 4. So negative 27 minus 4, that is negative 31. So 81 minus 31 is equal to 50. And remember, we're still trying to solve for a sub n, and yes, we're still on the same problem, and yes, it takes all the steps to solve the problem. Yes?
There's no possible way you can like condense all of that down. You have to like.
This is dual credit pre-cal, so no. Another way to do it, some people prefer to do it here before multiplying the factors. Like you could actually substitute with a 3 and a 3 and then substitute this with a negative 150. You could do that as well. That's another option. You can watch the video. So now here to solve for a sub n, this will be negative 150. And what is this 50 doing here to the a sub n? Multiplying, so we're going to divide by 3. And so a sub n is equal to negative 3. So yeah, I mean, if you guys think this problem takes too long, wait until you take part 2 of dual credit pre-cal. Yeah. No one said that we were going to give you an associate's degree for free, right? Or a good grade for free. Oh, someone told you that?
Well, it is free, but
I mean, okay, yeah, that's true. That's true. Without working hard. That's what I meant. Especially a college class or a dual credit class, you have to work for it. Dual credit pre-cal 1, it's not even that hard. Wait until you take dual credit pre-cal 2. Wait until you take calculus, if you have to take calculus. Yeah, things are not easy.
College classes, like you didn't make that even in
Math classes?
no, like
Okay. That.
I'm not talking about math.
Okay, no, yeah, I know. It depends on the professor. Okay, so anyways, are we done with the problem? No, we're not. We're not. So last thing we need to do to find the polynomial is, now that we know what a sub n is equal to, and then could you guys tell me what was the polynomial? It started with x to the 4. What else? And what else? Minus what? Okay. So then here we need to distribute the negative 3. So that will be negative 3x to the 4th. And then negative 3 times negative 3, that's positive 9x squared. And then negative 3 times negative 4 is positive 12. Now we're done. Yes, now we're done. So that is the answer to the problem. Okay, when is this class over? At 3:10. So I'm gonna pause the video, but once you guys leave, I'm gonna finish recording it. So the next slide, we're gonna look at rule of signs, and this was created by a French mathematician. I am not sure about the pronunciation, but I will just gonna refer to it as the Cardinal rule of signs. And so this rule of signs provides even more specific information about the number of real zeros. That a polynomial can have. And this rule is based on considering variations in sign between consecutive coefficients. And here our keyword is going to be variations in sign. So what we're going to be looking at is when we go from a positive sign to a negative sign, or a negative sign to a positive sign. So to begin with, we have here the sign of the leading coefficient is positive. We don't see a sign, but we know it's positive. So we go here from positive to negative, so that will be our first variation. Now we stayed from negative to negative, so there's no variation there. And then we go from negative to positive, so that will be our second variation. And then we go from positive to another positive, so there's no variation there. And then from x to -3, there is one variation. We went from positive to negative, so that will be considered our third variation. So let's just go over the definition of the rule, or the explanation. So it says here that the number of positive real zeros will be either the same name as the same number as of sign changes. So for our example, positive real zeros, we could have 3 because we had 3 sign changes. Now there is an or, so we need to look at statement B, and so that will be or less than the number of sign changes by a positive even integer. So what this implies is that we're going to be subtracting. So less than, so we're going to subtract. And what we're going to subtract are even integers. And so even integers will be 2, 4, 6, and so on. So for example here, we started with 3. So if we subtract 2 from 3, we will get 1. If we subtract 2 again, we will get -1. Now, could we have -1 positive real zeros? No. And here we're talking about the quantity, about how many real zeros do you have. If the theorem doesn't say that x equals to 3 is a 0 and x equals to 1 is a 0. That's not what this theorem is about. So in fact, it's just talking about possibilities. Possible positive real zeros. We could have 3 of those, or we could have 1. So what you could do here is you count the sign changes, and then you just keep subtracting 2 or even integers until you reach a negative number, because we cannot have negative possibilities. So now let's look at for negative zeros. And that is the next part of the definition, or the explanation that we have here. So for negative real zeros, we're going to have to find f of negative x. And so I'm going to do that with the same polynomial. And this will be f of negative x. We do that by substituting every x with a negative x inside parentheses. And so we know here that if we have an odd power, the result will be negative. So in other words, negative x raised to the 7th power, it will be negative x times negative x times negative x times negative x times negative x, and 2 more. And so here, if you count the negative times negative is positive, negative times negative is positive, negative times negative is positive. So if you were to multiply the first 6 of those negative x's, you will get a positive solution. But there is one more negative here. So that is why our answer for this expression will be negative x to the power 7. So now when we multiply that times 3, times this coefficient, we will put the negative sign in front of the 3. So this will be negative 3x to the power 7. Now here we have another odd power, so the answer that will come from there is going to be negative x to the power 5. Now that times negative 2 will give us positive x to the power 5. The next one, we have negative x to the power 4. Now in this case, we have an even power. So because of that, negative x to the power 4 is going to be positive x to the 4th power. Now we need to take into consideration that we have a negative in front of it, so that will make our answer negative x to the 4th. The next thing will be negative x squared, and so that would be positive x squared. So positive x squared times 7 is positive 7x squared. Then we have negative x, and last thing is negative 3. So now I'm going to go ahead and count the sign changes, and remember these are the sign changes for f of negative x. So we go here from negative to positive, that will be our first sign change. Then we go from positive to negative, so that will be our second. And then we go from negative to positive, so that will be a third one. And then we go from positive to negative, so that will be a fourth one. And then we remain with a negative sign, so no more sign changes. So in this case, we have a total of 4 sign changes. So now this is going to tell us the possible negative real zeros. And for this one, we have 4 sign changes. And remember how we need to keep subtracting 2 or subtracting positive even integers. So if I do that, 4 minus 2 is 2. 2 minus 2 is 0. So for this problem, we have that possible positive real zeros, we could have either 3 or 1. And possible negative real zeros, we could have 4 or 2 or none. So now let's go to the last slide. And here we have the same explanation. it is the previous problem. So if you have 3 sign changes, that means you could have 3 positive real zeros or 1. Now, that is the problem that we just did. If we look at this one, here we have 1 sign change going from positive to negative, so that is the first one. And then we have another one here going from negative to positive, so that's the second one. So we have 2 sign changes, so that means that we can have 2 positive real zeros, or if we subtract 2, remember how we have to subtract an even integer, the answer will be 0, meaning none. So we could have either 2 positive real zeros or none. For the last problem, we have here only 1 sign change that happened here from negative to positive, only 1. And so in this case, we can only have 1 positive real zero. Remember, if we subtract 2 from here, we will get a negative 1. And here we're counting possibilities, so we cannot say that we have negative 1 possibilities. So let's do the last problem of this section. So we're going to use the determine the possible numbers, remember, possibilities of positive and negative real zeros. So let's count the sign changes here. You notice that all the coefficients are positive. So the possible positive real zeros, since there were no sign changes, will be 0 or none. So that tells me if we were to use the rational zero theorem for this one, let's just do it quickly. We get the factors of 4. So that's plus minus 1, plus minus 2, plus minus 4. And then we divide by the factors of the leading coefficient, which is 1. So those are plus minus 1. Now, what we have here is that we will have all these numbers divided by 1. But since we know that they cannot be any positive real zeros, that kind of reduces my options. Instead of going from 2, 4, 6, remember, reduces my options, so I can get rid of all the positive ones and just say that the possible rational zeros will be only negative 1, negative 2, and negative 4. So that will be a useful way to find, to shorten your work if you didn't have a graphing calculator. Now let's go ahead and find the possible negative real zeros. And so for us to do that, we need to find f of negative x. So remember, we need to substitute every x with a negative x. So here, after reducing it, remember, odd power, so that will be negative x cubed. Even power, so that will be positive x squared, so this will be plus 2x squared. Here we have positive 5 times negative x, that will be negative 5x, and then we have a plus 4. So let's go ahead and count the sign changes here. So we have negative to positive, that will be 1. Then we have positive to negative, that will be 2. And then finally we have negative to positive, and so that will be 3. So now in this case, going back to answering this question, how how many possible negative real zeros can we have. It will be the number of sign changes. Remember, we have to subtract even integers. So if we subtract 2 from 3, we will get 1. And we can't do it again because remember, that will give us to a negative possibility, and that is not possible. So going back to this polynomial, this is of degree 3. So remember, we should have 3 zeros. So what that tells me is that we cannot have positive real zeros. So what that will tell me is that we are going to have 3 negative zeros. So this concludes the video for section 2.5, part 2. If you do have a question, please send me a message through Edmodo. If not, you could stop by Monday morning or Tuesday morning or Wednesday morning or Thursday morning. Just make sure you get those questions answered before the test. Also, I want to remind you that Monday we will have a review session after school from 4 to 5. And so that will be on Monday.